And our new definition for the day is the determinant. Okay? So we're going to figure out what determinants are. If you have identity matrices, which are square matrices where the main diagonal is 1s, these are matrices that always have a determinant of 1. And these identity matrices are nice because if you go A times the identity matrix, you get A. If you do I times the identity matrix, you get A. They're like multiplying by the number 1. You multiply any regular number by the number 1, you get the same thing. In matrices, if you multiply any matrice by a square identity matrix, you get exactly what you started with. So what is a determinant? Well, here's the algebraic definition of a determinant. And we write determinant either with det in front of a matrix, like determinant of this, or we use straight bars. So you know how a matrix has sort of square brackets? If you have straight bars, that's saying, can you find the determinant? And the algebraic definition of the determinant is that it is AD minus BC. The way that I remember this is with a visual. It is this diagonal, A times D, minus this diagonal, B times C. So the diagonal going forward, left to right is positive. The diagonal going backwards is negative. And your determinant is equal to that value. So knowing that math, what I always do when I'm figuring these out is I don't write out the formula. I just do this arrow like that. What's 4 times 2? It's 8. I do this arrow backwards. What's 3 times negative 3? That's negative 9. And so my determinant is going to be 8 minus negative 9. Which is equal to 17. I find the visual definition easier to remember than the actual letter definition. Because I'm like, oh, how did I, okay, if it's ADB minus BC, oh, where did I put A? Pretty sure you'd get A right, but then you'd be like, oh, did I move B to the left, or did I put B down? What did I decide? How would I do that? So the visual definition makes it much easier to remember. So here, going this way, I get 36. Going this diagonal, I also get 36. If I subtracted those, I get 0. And determinants are going to be important for finding inverses. And inverses are what we use instead of dividing in matrices. Notice we learned how to add, we learned how to subtract, we learned how to multiply, but we never learned how to divide. We're going to want to do mathematics with matrices, and instead of dividing, we have an inverse. And inverses cancel things like with functions. Inverses cancel each other out. Like what's the inverse of x squared? Square root. And if you square root an x squared, you just end up with x. So inverses cancel each other out. We're going to find out that when we use inverses in matrices, inverses give us the number 1 when you multiply them together. When they cancel each other out, it's like dividing. 5 divided by 5 is 1. So an inverse times a matrix is going to be the identity matrix in the end. Does it make sense that you can only find the determinant of a square matrix? Because that diagonal doesn't quite work with other ones. We're mainly going to be asked to do 2 by 2s by hand, and sometimes 3 by 3s actually. We're going to do 3 by 3s by hand as well. And these matrices that have a determinant of 0 They're called singular matrices because an inverse does not work. You ready for a very not nice looking formula? Here's the formula for the 3 by 3 matrix. Perfect, thank you. Yeah. So, the determinant of a 3 by 3 matrix is you would first take A, and if you ignored everything in that column of A and B, you take A and multiply it by the determinant of what is left as a small one. Then you'd switch signs and subtract B, and if you got rid of everything that was in the rows and columns of B, and multiplied by the determinant of what is left, and then you would go to C, cancel everything out in that row and column, and multiply C by the term that's left. But I'm going to show you an easier visual definition to figure out the determinant. So, this is the easier definition. I'll erase the lines. No, I will not. I will pretend to erase the lines. I will keep pretending. Are the lines on yours already? So what you do is you take your matrix and rewrite column 1 and 2 again. That allows me to draw 3 diagonals in the positive direction. And if I take all 3 of those and add them together, I'd get 1 number. And it would allow me to draw 3 diagonals in the negative direction. And if I would take all 3 of those and add them together, then it's the same thing. Whatever number you get in the blue, subtract whatever number you get in the red, will be your determinant. I'll put a big negative in front of this one. I think that's an easier way to visualize and figure it out rather than remembering this formula. But you do have a visual for this formula as well, where you start with A, cancel everything out in those row and column, multiply by the determinant that's next, left. Then move over to B, cancel out its row and column, and multiply by the determinant that's left, but that middle one is negative. And then same thing when you get to C, cancel out its row and column, and multiply by the determinant that is left. And then these ones, you still have to do that diagonal for the little ones, right? Like if I wanted to figure this out, I'd go EK minus FH. So let's do one with the diagonal method. So what I would do first is I'd take column 1 and column 2 and rewrite column 1 and column 2. Try to space it out so that they're the same spacing as the numbers before. So when you make those blue diagonal lines and you make those red diagonal lines, they match up nicely. Two times 2 times 2, that'll be 8. Oh, I love ones with 0 in it, because when you multiply all 3 of those numbers, you're going to get 0. And then 4 times 1 times 1 is 4. Adding those all up, you get 12 in that set of brackets. On the red side, you'd have 16 plus 0 and a negative 2. That adds up to 14. Then you do your 12 minus your 14. This one would have a determinant of 2. There's also a determinant button on your calculator. So I'm going to take this matrix that we just had here, and I'm going to type it into my calculator. 2, negative 1, 4. So here we go. I'm going to go to second matrix, go over to edit. It was a 3 by 3. 2, negative 1, 4. 2, negative 1, 4, 1, 2, 0. 2, 0. And 2, 1, 2. 2, 1, 2. So I have my matrix built in my calculator. It's matrix A. And if you're on your regular screen and you go to second matrix, in between names and edit, which are the ones we've done so far, in between them is math you can do. And the very first one is determinant. So if I want to find the determinant of matrix A, push enter, it tells me it's negative 2. Same answer that we got. I'd like you to try the second one on your own and see if you can find the determinant. How did you do? Did you get 30? Add up your main diagonals and get 12. Add up your other diagonals, get negative 18. Subtract them and get 30. Now on your calculator, so if we go back to matrix, and this is on the next page, and we go to math, like, first one was determinant. I wonder if that's dimensions. Dimensions of A? Oops, hit the wrong button. Yeah, it's a 3 by 3. I don't know when you would want to use that. I think it's pretty easy to count the rows and the columns. But you could use the math on your calculator. Ones that we're going to, that are like, again, the transpose, I don't think you'll use that very much. That's just switching your rows and columns. It's pretty easy to do. I don't think you need a calculator for that. But that's what that second one is. We're going to use the determinant one for sure. Moving down, we're going to use the ref one. And even more than the ref one, we're going to use the ref one. So there's the ref one and the ref one. We're going to use the ref one more than the ref one. Okay? That one's going to be actually really quite cool later on, but right now you don't know how to use it. We don't know what it does. I'll show you later. Okay? I know what you're laughing at. I'm going to try to get off of this screen as quick as possible. Yeah. The realization that the way that you said ref wasn't that funny, there was something else. Okay, good. We're all good. Okay. Inverse. So we can't divide, but instead, if we have equations, we can do inverses. So the inverse of a square matrix Other matrices don't have inverses, unfortunately. Only square matrices have inverse, is denoted by A inverse. And the product of a matrix and its inverse, no matter which order you do, whether the inverse is in front or the inverse is in back, that's important because in matrices you learned that the order of multiplying is important. Sometimes you can do A times B, but you can't do B times A. So the order is important. But in this situation, when you multiply by an inverse either in front or behind, it's equal to the identity matrix. And how do we find an inverse? Well, with a 2 by 2, you find your determinant, then do 1 divided by your determinant, and the main diagonal gets switched, and the other diagonal you just add negatives in front. This is kind of weird. We will figure out other ways to find inverses. This is method 1. This is the formula for finding an inverse. So you'll need the determinant. So first of all, can you see that your determinant will be 6 minus 5, which is 1. Main diagonal is 6. Backwards diagonal is 5. Subtract them, and we get a determinant of 1. So the inverse then is 1 over 1. The 3 and the 2 switch places. The negative 1 and the negative 5, the 1 and the 5, just add a negative in front of it. So this will be like one of the first things you'll have to memorize in this unit is how to find an inverse. So the 1 over 1 is just 1, so we could write it like this. And if you check it out, I have it here, okay? A times A inverse. If I take 2, 1, 5, 3, and multiply it by this, okay? I will start by circling row 1, column 1. If I turn row 1 and crash it into column 1, do you see that you get 6 minus 5, which is 1. So what we want to get, the identity matrix. If I take, delete these. If I take row 1, column 2, that will give me this answer, right? Row 1, column 2 answer. See, if you turn 2, 1 sideways, crash it in, you get negative 2 and 2, which would be 0. Nice. If I take, to find this one, it's in row 2, it's in column 1. Take a 5, 3, crash it into 3 and the negative 5, I get 15 and negative 15. That'll give me 0. And finally, if I want to find this one, which is in row 2 and column 2, 5 times the negative 1 will be negative 5, 3 times the 2 will be 6, add them together, I get 1. So whenever you get the inverse will show up, and you multiply them together, you will get the identity matrix. I'm going to go to my calculator here, just show you, like, you're like, oh, that would be super helpful if the inverse button was listed in the math, and it's not. Do not worry. I'm going to go edit. Let's make B a 2 by 2. And let's write the one that we just had. Let's see what, 2, 1, 5, 3. Is that what we had? 2, 1, 5, 3. Quit. I go matrix, and I select A. And I want the inverse. No, that's squaring it. That's going to be bad. I don't want to square it. Oh my goodness. I'm struggling right now. Thank you. There we go. Now I hit the inverse button. Oh. Whoa. I put it into B, didn't I? Yeah. There's the inverse of the 3 by 3. But Doesn't make you believe me, I'm telling you the truth. B. All that struggling to hit the inverse button, and I had the wrong. 3, -1, -5, 2. Our same answer. So that little -1 that's in our regular buttons, you're allowed to use that for inverse on matrices. Super, super cool. Okay, find the inverse of this second one. Here's the first one. Find the inverse of that second one on your own. Now, it doesn't happen in this case, but if you figured out the determinant first and it was 0, then you would just say inverse does not exist. Right? How did you do? And it's okay, I'm happy. I actually like this better, personally, with the fraction out in front. You can put the fraction in. That's how it, oh, I do want to show you something cool. I'm going to put this one in, just because it's cool. Second matrix, going to go edit. I'll edit, oh, I don't want to edit A. Second matrix, edit. I'll do B again, because it's already a 2 by 2. And then -3, 2, 0, -1. Make sure if you're using negatives, you're using the actual negative sign. And if I do second quit, and I go second matrix, and I take B off, I'm just going to highlight this, and just highlight that from before to save myself time. And I push enter, but it's got all of those decimals, right? If you had decimals in a regular question and you wanted a fraction, you would go to your math button and say, I'd like to change that to a fraction. Is that possible? Yes, it is. That's kind of cool. So you can have that as a much nicer answer in the end. But for me personally, right, if I was, here we go. If I was back here and wanted to check if this worked, I would take this matrix here, right? I'd take this matrix here and I'd put it right beside it. And then I have a choice. I could either multiply and do all my mental math with fractions, or I could do these two things first, and then multiply by a third after. And if you do those two things first, surprise, surprise, you get this. And then when I multiply by the third after, oh, I get the identity matrix with the ones. So, and the mental math is way nicer with whole numbers than it is with dealing with all those fractions all the way through. Now, I'm not going to teach you this is the idea that if your determinant is 0 and you have a singular matrix, because the formula has 1 divided by your determinant and we're not allowed to divide by 0, those matrices have no inverse. So there are some things that you can't divide by or get rid of in doing the math. For 3 by 3s, you're going to have to use the x minus 1 button. So you would type this into your calculator, push the f to the -1 button, then I'd probably push the fraction button, because it will just give you numbers like, where do I start? If you hit that fraction button, it makes your numbers very, very nice. I could show you the formula for finding the inverse of a 3 by 3. It's only like 5 pages long. It's really quite user-friendly. So if you'd like, you can look that up on your own and use that instead of the calculator. That's up to you. There's a method later I could show you that's kind of cool. That is doable without a calculator. But the actual formula, no. It uses a whole bunch of transposes and nothing. Yeah. I just remember it long, and I remember choosing not to ever remember. So why would we want an inverse? And you're probably like, I actually don't. I don't care whatsoever. Okay, I'm sorry. I'm excited about this. We can solve our system. We have really good methods for solving our system of linear equations. That sorry to burst your bubble in a 2 by 2 system are much better than using matrices. But I'm now going to show you how we can do the same thing using matrices instead. But first of all, can you see this would be really easy to solve with elimination? I would probably just subtract the 2. If I subtracted this whole thing, then I would get negative y equals 9. Oh, I've already figured out what y is. Yay. And if I know what y is, right, I can move that over to the other side and get, did I make a mistake in my, yeah, that looks good. Y is equal to negative 9. If y is equal to negative 9, then x would be, move this order to 1/2. Does it work? 2. No. Something went wrong. What did I do wrong? Oh, negative 1/2. There we go. X is negative 1/2. See if it works now. This would be negative 2. No. What did I do wrong? Negative 5? Oh, because this y would be negative, would be positive. Ah. So, yeah. And then we would over and be negative 20, and then divide by 4, x would be negative 5. See, it's always good when you solve something to like, hey, I should check if my answer is right. Because if it's wrong, probably means you did something wrong. And what was my biggest mistake? I was probably trying to do too much mental math in my head, not enough by showing my work. Some of you fall into that category at times. And you make mistakes. Okay, let's see, negative 5. This would be negative 20 plus 18, negative 2. Okay, just a little excited there. And here, if I plug negative 20 plus 9, it'd be negative 11, yes. So there's our answer, which took longer than I expected because of the number of mental math mistakes we made, but probably still didn't take very long to solve using either substitution or elimination. You guys are pretty good at that already. Now I'm going to teach you a new way that's a little bit longer, but it uses matrices. And I hope you enjoy it because the new way, if you have your calculator, will be really slick for 3 by 3 systems, 4 by 4 systems, 5 by 5 systems. Like if you had 5 equations with 5 unknowns, right? Like, strap yourself in. It's going to be a long night of solving with our other methods. And the matrices could be really quick, especially if you have a calculator. Okay? I mean, now you guys have like AI. You just solve this one. Okay, so we rewrite the system as a matrix A times a variable matrix X equals an answer matrix B. Do you see how matrix multiplication works? What if I take this times this? I would turn it on its side and crash it in. I would get 4x minus 2y. Is that not what our first equation was? 4x minus 2y. And if I took the second one and crashed it, I get a 4x minus y, which is what I had originally. What I want to do is I want to find out what x and y are. Here's the idea. If I can find an inverse of A, I could, right, here it is, I could multiply the front by A inverse. Because A inverse times A will be the identity, and the identity times anything, no matter what its size is, will just be what it is. Now what's really important here to notice, and this is hard for math students, is that, you know, like in our regular equations, just saying, like if I had x divided by 2 equals 3, how would I get rid of the 2? You would multiply this side by 2, and you would multiply this side by 2. And this is probably how you would show your work. And this is perfectly fine in regular math, but it would be bad in matrices. It would be bad in matrices because on the one side, I multiplied in front. And on the other side, I multiplied behind. And in matrices, where you multiply makes a difference. So it's important to notice that if I multiply in the front by A inverse here, I have to make sure that I multiply in the front by A inverse there. That's different. Because normally you would just be like, so technically if you did this, you lose a mark. Because that is not true. I can't just multiply. I can multiply both sides by A inverse, but this would be bad to write it this way. Because this one's in front and this one's in behind, and I would get into trouble. But if I write them both in front, this tells me that x equals A inverse B. So let's actually solve this equation using matrices. We already struggled and found the right answer, which is good to know. Okay. So we set up our coefficients matrix, we set up our variables matrix, and we set up our answer matrix. This is a 2 by 2 by 2 by 1, so this is allowed. Your answer is a 2 by 1, so that everything makes sense. Now we need to find our inverse, because if we had ax equals b and we multiplied by A inverse in the front on both sides, we would get that x is equal to A inverse b. We'd have to get our determinant. -4 minus a -8 will be 1 over 4. Switch the main diagonal, make the other diagonal negative. And personally, I would keep this 1/4 out in front. Because keeping that 1/4 out in front is easier math. Now you're going to have to multiply these two. This is a 2 by 2. This is a 2 by 1. We're going to get an answer that's a 2 by 1. And I kept the 1/4 out in front. So like -1 times 2 is 2, 2 times -11, -22, add those up, -20. For row 2, column 1, take row 2, turn it sideways, crash it in, add up the pieces, you get -36. Now if we put the if you put that 1/4 in, you get -5 and -9. That tells us our x value is -5. Our y value is -9. So I'd like you to try the next two on your own. I'll put up an answer. All right, how did you do on the second one? Did you find your inverse to be 1/5, 1, 2, negative 1, 3? And then when you multiplied, you got 1/5 of 5, negative 5, which means your x value is 1 and your y value is negative 1. Of course, if you solve this via your old techniques, it probably would still be quicker, right? That's okay. But it's kind of cool how this inverse thing is working, application-wise. And here's your last one. Okay. So a little bit not nice fraction here to begin with. Rearrange things. I'd multiply everything by 4. I'd move my 3x over. And then I could set up my matrix A, my matrix X, my matrix B. Did you get the inverse to be 1/7 of 4, negative 1, 3, 1? And then when you multiply it out, you get 5, negative 4. All right, that is where we're going to stop for today, because the next is just that you've got homework on the thing that I just handed out.